is one of the chapters in my dissertation. Also hearing a lot of diversity about different topics. I really have been doing this, and to add more to this, I'm going to be talking about gases or swamp gas. Before I start, I would like to explain a little bit why such an exotic researcher and an exotic university doing research here in Florida. I'm from Colombia. I went to Ohio State to do research on wetlands. I was really interested in do research in the tropics. And in Ohio there is a very good program in wetlands, so I went there and the things really didn't work out well, so we had to find a place to which we can ride closer to the tropics. It turns out to be Florida, so that was the fastest or the shortest way to do it. So that's how I end up or start coming here, and we start driving every 3 months to collect my samples until my advisor give me the notice or give me the news that he's already retiring from Ohio State, but he was taking a position here at the Florida Gulf Coast University, and of course for me that worked really well with my logistics, so that's the why of Ohio State. By the way, I would like to introduce the Everglades Wetland Research Park. This is at the Cabin Center in the Naples Botanical Garden. And this is the type of research we are doing. We deal with restoration, with carbon fluxes, which is part of what I'm going to be presenting today. Also methane emissions in created wetlands and coastal marine restoration. This is our webpage. I will invite you to go and visit it. We have a series of lectures about wetland topics, different wetland topics. There are some flyers, graphic flyers, that I would like you to take to some of your offices and spread the word. We're going to have really good lecturers. We're going to have Jorge from Louisiana State University, Jorge Eriksson from Denmark. He's also going to be teaching a course in systems ecology, so you can drop a lot of information there. So by now, I hope you're more familiar with my accent, so I'm not going to proceed with my topic. And we have that about 20% of the Earth's carbon pool is stored in wetlands. This is a huge storage or carbon sink, which is actually one of the greatest or more valuable wetland ecosystem services that we have nowadays. And just to illustrate that, this is the way that it's being stored under wet conditions and oxy conditions. The organic matter cannot decompose, so it's stored in the soil. So this is basically a soil profile or a peat core in the Corkscrew Swamp. However, the same conditions that allow this to happen also lead to the production of methane, right? So the organic matter is not decomposed under aerobic conditions, but under anaerobic conditions can be decomposed at a way much less efficient way and will lead to the production of methane. And the general problem with methane is that it can be 25 or have, it's 25 times more potent than carbon dioxide in warming the air. So we have these two things going on. It's good to cool down the earth, but it also can warm the earth at the same time. So how much or which will win, it's still debatable, which will be greater. And I just want to point out how these methane is produced. I'm not going to explain all these, I just want to focus and draw your attention to, here we have the different compounds, microbe communities, and also the different processes involved in the production of methane. And I just want you to notice that there's two pathways to produce methane. It's going to be either to acetate or to the reduction of carbon dioxide. So that's what it's going to lead to the production of methane. I'm going to back to this towards the end. And why do we care about methane, right? We have the methane or about 25% of the global emission of methane come from wetlands, which is the largest single source. And also, besides that, the recent variability in the methane in the atmosphere is being attributed only to wetland emissions. So we have noticed an increase in methane in our atmosphere, and it's due to wetlands. So that's why we care about wetlands in a global scale. Now, where methane is produced, and Bloom and his colleagues published this in Science in 2010, and they show basically where the methane is produced in the world. And this is due using satellite data. And we have that roughly 55% or a little bit more than half of the methane is produced in tropical and subtropical zones, right? And what to control this production of methane and these emissions? We know now that it's mainly the water level or the presence of water that will lead to anoxic conditions, also the temperature that will give the optimum for the microbes to start working on this organic matter, and also the source and quantity of organic matter that will lead to different pH or different substrata. For instance, there will be or even more acetate or CO2, so that will lead to the different methane emissions. However, most of our current understanding of these processes come from the peatlands at high latitudes. So we know a lot about what's going on in wetlands in Canada, in Europe, in Russia, but we don't know much about wetlands in tropical and subtropical regions. And we know that now that this is more than half of the methane emissions come from there. These same researchers, Bloom and his colleagues, they, based on this study that they do with satellite data, they kind of conclude that water height will explain most of the methane, of the variability in the methane emissions. Whereas temperature will just explain a little bit. And this kind of contradicts what we know from the boreal or the high latitude wetlands. Their temperature exerts a strong control on methane emissions, right? We have this huge contrast between winter and summer, and of course temperature will make some, or will explain a lot. But here we kind of have like an average temperature that doesn't vary too much, so the microbes are okay to work in these conditions. So this contradicted what we know, right? So this is as much as we know nowadays about methane emissions in different latitudes. Now let me put this methane emission in the perspective of here of Southwest Florida. And I know you're familiar now with the comprehensive Everglades restoration plan. So basically the main goal of this is to restore the natural flow of the Everglades, among others. So we have the historical flow on the left, the current flow, and this is what is planned to do. So this plan, restoration plan, will lead to some change in the water level. And changing the water level somehow will also change the rest of the conditions that you need to produce methane. So we need to understand, or to better understand the current methane emissions as with the ecosystem as we have it right now, in order to get a better insight of how the ecosystem is functioning. Right? So we can compare what's going to happen after we do these restoration initiatives. And so, and we can also see or better assess the ecosystem services. So we're talking about a lot of carbon sequestration, but changing the water level will also change somehow the methane emissions. So we need to know what's going on and what's going to happen. And this, of course, is a very good opportunity for us doing research to try to gain or expand our understanding of methane emissions in warmer climates. So having this in mind, we set as an objective for this part of my dissertation to measure methane emissions from 5 different wetland plant communities that will have different idle periods. And this will represent also a distance successional stage of a pristine wetland landscape here in this part of the Everglades region of southern Florida. More specifically, we wanted to see what would be the variability between this plant community in terms of methane emissions, and also what will be the seasonal variability between these plant communities. So we're doing, we plan to do, or we're doing this, but we're doing this right now in the Corkscrew Swamp, which is the Rancho side. It's part of the Corkscrew Regional Ecosystem Watershed. I hope you're familiar with this. I guess you are. And with the Corkscrew Swamp. So what we did is that we went out there and took a different size along this gradient of idle people. So we have a pine flatwood, which is our control site. We want to see what's going on in the outland. But then we start moving towards longer idle periods. So we have a wet prairie side, pond cypress, which I still don't know if it's still the same both cypress, but we're gonna call it for this presentation the pond cypress, which is a smaller cypress type, the ball cypress, and there we have we separate that into different plant communities. We have a hammock and a hollow side. I'm gonna show it in a minute. And then we have a leaf. So I'm gonna skip fast so you can have an idea of the size. On the left, this is the dry season. On the left bottom, and on the right bottom, we have the wet season. And up in the upper part is like a panoramic view with some of the most common species. So that's going to be the same format for all the sites. So I'm just going to see deep blue. This is our ball cypress. This is the hammock side. This is the hollow side of the same ball cypress. This is what we call the pond cypress, or wet prairie, and finally our pine flatwood, or our control. So we went out there and collect methane in these 4 different times of the year. So we started in 2011. This goes, no, sorry, 2010. This goes to 2011 to 2012. So the gray bars indicate the sampling periods or the sampling time we did. And we have the different water depths and the size. And dotted line means the soil, or represents the soil. So we have the loop having a higher water table, a longer idle period. Then comes the hollow of the ball cypress. And we have wet prairie, pond cypress, and the ball cypress on the hammock side, having very similar idle periods. However, when the wet season stops, and with the transition with the dry season, there's some difference that might account in the soil, that might account for different in the idle period. So that's going to be our gradient. That represents our gradient weighting. So I'm going to explain fast the method that we use. We use this highly technical or very developed instrument, which is basically just a simple plastic box that we got on Target or Walmart. So we just put a tube in it, so we will have like the atmospheric pressure. We won't have like, the pressure building up in them, so plants can actually, or whatever is going on in the soil can breathe. So it's not going to be a stop. And when it was dry, or the water level was less than 10 centimeters, we use the frame and we just put the chamber on top of it and seal it. We collect sample for 30 minutes, 35 minutes. And when the water level was higher, we just use this floating, this modified version, just put pool noodles on it and just make it floating. That was our chambers. We did at least three times of the day. We did it during the morning, noon, and afternoon. So we went there for 30 minutes. We collect samples with a needle, and every 5 minutes, right? And we put it in a vial, and we took it to the lab and analyzed these vials in a gas chromatograph, right? So what we will have is something like this. We will have the concentration over time, and then we draw a regression line on these measurements, and that the slope of that regression line will be our rate of emission. Then we convert that rate of emission into the methane flux. That's how we get the methane flux process. And this is the statistical analysis used to test the difference between the sampling times. So now I'm going to move to the results. And here we have the different methane concentration at the 3 different times of day: morning, noon, and afternoon. And we have them for each different site during each of the sampling periods that were June, September, December, and March. The ones that are highlighted in blue of these sampling times means periods or sampling times where they were watered or standing water. So it can help to at least to interpret the data. And the first thing I want you to notice is the difference in the scales. Not all of the sites are following the same scales. So they're on their own scale, so we can see actually here the differences. There were some difference in sampling times, mostly in the deep slough, and we have some of the ball cypress and wet prairie, but we cannot notice, we couldn't find a pattern in this. So for the deep slough, we found difference between the noon time when there was water in it, and when it was dry, the afternoon time or sampling exhibited more methane emissions. Whereas in the ball cypress and wet prairie keep presenting more or less methane emissions during, or different methane emissions from the other ones during the afternoon. So we couldn't figure out a pattern. So our first conclusion was that methane emissions are highly variable during the day and very different. So that led us to go back to what Bloom found. I mean, we're talking about the same water level during the same day, right? So what's the difference between these emissions? And we also noticed that our control saddle upland work as a sink of methane instead of intermediate methane, was captured methane, right? Which was not surprising for being upland, but we also find this behavior in other of our wetland sites. And that's not very common to be reported like the wetlands. Instead of intermediate, it's sinking methane. This is the variation or the methane emissions now plotted on the same scale. And we can see that the deep slough and the wet prairie were the ones that were emitting way much higher methane than the other ones. And here we can show our first pattern, and is that the plant communities that are not woody communities or not forests were the ones that were emitting more methane. Is that kind of started heading us or leading our results. So we select these 2 plant communities and wanted to see what's going on in terms of the water level and also the temperature of the soil. So here we have the methane emissions during the 6 different times and the water level in the land. So for the deep slough, we noticed that when the water level was higher, the methane emissions were higher, right? But when they were lower, which is here, they were very close to the higher methane emissions, right? So it's not clear what's going on there. For the wet prairie, it was more clear that it was some sort of a pattern. But actually, it was not very clear here. So you can see that when the water level was just starting, we have the highest methane emissions. When the water level was a little bit higher than at the beginning, they started reducing, and towards the end it was reducing. So we couldn't find a clear pattern of what's going on. So these guys reported that the water level was very important in the methane emissions, or explain the variability. We couldn't see this in our on-site measurements. And we wanted to see what's going on with temperature. So we know for boreal wetlands that the temperature is very important. This recent study says it's not as important as it's going to be for the boreal wetlands. And we found that for the deep slough, there seems to be a good correlation between temperature and methane emissions. But that correlation was not clear at all for the wet part. So at this point, we didn't know what's going on for sure. I mean, we have different pieces of information from different wetlands of the world. So at least we can draw some preliminary conclusion. This project is still going on. Still have a year to figure out what's going on. Hopefully I will be able to. But in summary, non-vascular dominated plant communities will have more methane emissions than the ones that were of wooded communities. And also that methane emissions respond differently to water levels and soil temperature in different plant communities. So the response that is being reported is not probably the exact same for all of them, these plant communities. Now some future directions. We already started increasing the frequency of our sampling. For now here I can go whenever I want. I'm trying 2 days to do something. So we increasing the frequency of sampling. We can now have like a small resolution of what's going on there. And also we want to know more about what's going on in terms of the organic matter. So what is the role that this organic matter is playing here? And for that we have an hypothesis. We think that the importance of these two methanogenic pathways that I mentioned at the beginning, they were shifting or they were changing throughout the wet period. And there's some indication of that happened in Alaska, in wetlands in Alaska, and also in rice paddies in Southeast Asia. But it hasn't been proved or tested in natural wetlands in tropical settings. So that's something that we're thinking about, or something that we're thinking about to do or go for as to help to explain our data. And finally, I would like to thank the people that have helped me, an institution that found my research and my presence here. And I would like to give a special thanks to Jorge from Corkscrew Swamp, still here. She's been very helpful with all the logistics and helping me setting up all the sites. Every time I go sampling, and she's there to help me with all problems. I have problems that.